Welcome to our midterm presentation. This is Team Datum, and we're presenting a shared scanning file service. The problem area within Hadoop that we're attacking is the area of expensive I/O. So expensive I/O is some overhead that we see as an opportunity to get rid of. Concurrent queries, as they run within Hadoop today, these MapReduce jobs, they perform independent file scans even when they're accessing the same data sets. So there's no sharing there, and this redundant I/O is costly, so let's take a look at getting rid of that. What we're talking about is a shared scan. It's got its own challenges. First, we can't take a naive approach where we just stage files for sharing because they're so large it wouldn't be feasible. So we take a look then at sharing at a block level and doing it opportunistically. And remember, our goal here is interactive big data analytics, so we need to reduce the worst case response time. And finally, we have to fit into the Hadoop architecture. We've gathered insight and we have an approach, and we took quite a bit of inspiration from the Circumflex paper. And what we have here is a realization that data is not ordered, so that allows us to look at the data as a circular buffer or as a ring of blocks as we have here in the diagram. So the idea here is that multiple requesters for this file can start sharing at any point on the ring as long as they circle back around and completely read the file. So that's our fundamental approach here. We've packaged up our solution into a file service module. It's a non-blocking, event-driven architecture. So frankly, we've put quite a bit of effort into the design and the implementation here, hoping it's going to pay off in some follow-on milestones. So we have what we think is a lightweight and scalable approach. Our preliminary results here show some good news for us. We have 3 tests that we run. A simple test just reads the file with a buffered file reader. We perform that exact same read concurrently. We use 20 threads, and the worst case response time was 13 seconds. Then using our file service and using the opportunistic sharing on that ring that I just described, we get a worst case response time of about 5.6 seconds. You can see here that our file service module has a very simple interface. We have 2 main methods, open and shutdown. When you open a file, you specify the path and an observer. The observer is then notified with events when it opens for each line, that's the on next, and then when it closes. So a file handle is communicated here, but it's just object identity is what we use for file handle. So if you look at the file service in use, you'll see that it's primarily constructing your observer, how you want to handle the file events. So you construct an observer and then you just ask the file service to open, and it will immediately call the on open. You'll get an on next for each line, and when you've read the file completely, an on close is signaled. So that's as simple as it gets. And then the file service implementation, we use the standards within the Java runtime for the executor service and the fixed thread pool. Note here that our non-blocking architecture only used 8 threads. So in a growing system with potentially say 1,000 users, we don't want separate threads for all of those. So we've taken that kind of scalability into consideration here. So let's see a quick example. Racing the clock. I'll hit run here. So this demonstration is the 20 tasks, they all completed. The worst case response time was just over 4 seconds. So we've completed our first milestone. We feel that we're positioned very well for the follow-on milestones. Here are our references. Thank you very much for watching our presentation, and we sure hope that we get to present to the class. Thank you.